Have you ever wondered how digital systems keep track of time and sequence? Well, the heart of such operations lies in a component known as a synchronous counter. These are digital counters that use a common clock signal to trigger simultaneous state transitions in all its flip-flops. Now you might be wondering, what's a flip-flop? Simply put, a flip-flop is a fundamental building block of digital systems. It's a type of latch that has two stable states, representing either a 0 or a 1, and it can be triggered to flip from one state to the other. So in a synchronous counter, all these flip-flops share a common clock signal, and they change their states, or flip, at the same time. This is in stark contrast to ripple counters, where each flip-flop is triggered by the previous one, causing a ripple effect that can lead to propagation delays. This simultaneous state transition in synchronous counters ensures a well-defined sequence. And the beauty of it is that it also allows for parallel loading of initial values. That means the initial count can be loaded into all flip-flops at once when a parallel load signal is activated. And why is this important? Well, it makes synchronous counters faster and more reliable than ripple counters. Their timing behavior is determined by the clock signal, and there's no cumulative delay to worry about. However, synchronous counters are not all roses. They are often more complex to design compared to ripple counters. The use of common clock signals and parallel loading does add a certain level of complexity. But the advantages in terms of speed and reliability often outweigh this complexity. For instance, consider a 4-bit synchronous binary counter. Each flip-flop represents a bit, and the counter advances its count on each rising edge of the clock signal. The design steps for such a counter would involve determining the number of flip-flops, selecting the type of flip-flops, designing the combinational logic, implementing parallel loading, connecting the flip-flops, and then simulating and verifying the design. So that's a brief introduction to synchronous counters, but what makes them so special? Let's delve deeper. Now, what sets synchronous counters apart from others? Well, their distinguishing features lie in their unique characteristics. First off, they operate on a common clock signal. This means all flip-flops in a synchronous counter are triggered by the same clock signal. The counter moves to its next state with each rising or falling edge of this clock signal. This synchronization eliminates the ripple effect seen in other types of counters. Secondly, synchronous counters support parallel loading of initial values. When the parallel load signal is activated, the initial count is loaded into all flip-flops at once. This feature allows for quick initialization of the counter to any desired state. A key characteristic of synchronous counters is the simultaneous state transition. Every flip-flop changes its state at the same time, making sure the counter goes through a well-defined sequence of states. This simultaneous action eliminates issues of propagation delay that you'd typically encounter with ripple counters. Synchronous counters also promise more reliable timing. Their timing behavior is more predictable compared to ripple counters, as there's no cumulative delay. This feature is crucial in applications where accurate timing is paramount. However, it's worth noting that synchronous counters can be more complex to design than ripple counters. The use of a common clock signal and parallel loading adds a layer of complexity. But don't let this deter you. The benefits in terms of speed and reliability often far outweigh this complexity. Imagine a 4-bit synchronous binary counter, where each flip-flop represents a bit. The counter advances its count with each rising edge of the clock signal, and all flip-flops change state simultaneously. This is the kind of efficiency and precision synchronous counters offer. So while synchronous counters may require a bit more work in the design phase, the payoff is a faster, more reliable counter. It's this combination of characteristics that has led to their widespread use in digital systems. Though they might be complex to design, the benefits of synchronous counters definitely outweigh the complexity. Let's take a real-world example to understand this better. A 4-bit synchronous binary counter. In a 4-bit synchronous binary counter, we have 4 flip-flops, each representing a bit. The counter will advance its count at each rising edge of the clock signal. This means that when the clock signal transitions from low to high, our counter will increment its value. Imagine the counter as a series of 4 interconnected boxes, each labeled Q0, Q1, Q2, and Q3, from right to left. These are our 4 flip-flops. Each box has 2 outputs, one that represents the current state of the flip-flop, and another that determines the state of the next flip-flop. As the clock signal rises, the first flip-flop, Q0, toggles its state. If it was 0, it becomes 1, and vice versa. This change in state is then reflected in the second flip-flop, Q1. However, Q1 only changes its state if Q0 was already in state 1 before the clock signal rose. This pattern continues with each subsequent flip-flop. Q2 will only toggle its state if both Q1 and Q0 were in state 1 before the clock signal rose. Similarly, Q3 will only change its state if Q2, Q1, and Q0 were all in state 1. In this way, the 4-bit synchronous counter will cycle through a binary count from 0 to 15, or 0000 to 1111 in binary, with each cycle of the clock signal. This is why we refer to it as a binary counter. Keep in mind that this is a simple example, and actual synchronous counters can get much more complex, especially when they include features like parallel loading or are designed to count in sequences other than binary. But even with this simple example, you can see the power of synchronous counters. They are fast, reliable, and capable of handling complex counting sequences. They're like a well-oiled machine, with each part working in perfect harmony with the others. So that's how a simple 4-bit synchronous counter operates. How about designing a synchronous counter? What steps do we need to follow? Firstly, we need to determine the number of flip-flops. For an n-bit synchronous counter, we require n flip-flops. Each flip-flop represents a single bit in the counter, so if we're designing a 4-bit counter, we'll need 4 flip-flops. Next, we select the type of flip-flops. The choice depends on the specific requirements of the counter. D flip-flops are commonly used because they can be easily configured to operate in the required modes. Once we've chosen our flip-flops, we need to design the combinational logic. This involves determining the logic equations that control the inputs to the flip-flops based on the desired counting sequence. The logic equations are derived from the truth table of the counter. Parallel loading is another important aspect of synchronous counters. If we want to incorporate this feature, we need to design the logic that allows for parallel loading of the initial count into all flip-flops when the parallel load signal is activated. Next, we connect the flip-flops in a cascading fashion. We also connect the common clock signal to all flip-flops. Remember, in a synchronous counter, all flip-flops share the same clock signal, ensuring that they all change state simultaneously. Finally, we simulate and verify our design. This is a crucial step to ensure that the counter behaves as expected. We need to verify the timing, ensuring that the counter advances on each rising or falling edge of the clock signal. We also check the count sequence to confirm that the counter goes through the expected sequence of states. Designing synchronous counters can be a complex task due to the need for common clock signals and parallel loading. But the benefits in terms of speed, reliability, and predictable timing often outweigh the complexity. These steps should guide you to design a simple synchronous counter. Now that we understand how synchronous counters work and how to design them, where are they used? Synchronous counters are the unsung heroes of our digital world. They quietly hum away in the heart of the technology we use every day, ensuring that everything runs smoothly and in sync. They are found in a multitude of applications, but let's focus on a couple of key areas: microprocessors and digital signal processors. In microprocessors, synchronous counters are used for a variety of tasks. They keep track of the execution sequence of instructions, manage the timing of data transfer between different components, and control the operation of the processor's different subsystems. With their simultaneous state transition and reliable timing characteristics, they provide the precision and reliability that microprocessors need to function effectively. Digital signal processors, on the other hand, use synchronous counters to manage the sequence of operations and the timing of signal processing tasks. They ensure that the digital signals are processed in the correct order and at the right time, which is crucial for the proper functioning of these systems. But it's not just microprocessors and digital signal processors. Synchronous counters are found in a wide range of digital systems, from simple digital clocks to complex computer systems. They are used in telecommunications equipment, digital cameras, and even in spacecraft navigation systems. Their ability to eliminate propagation delay and provide reliable timing makes them an indispensable part of these systems. In summary, synchronous counters are a type of digital counter that use a common clock signal to trigger the simultaneous transition of all flip-flops in the counter. They are characterized by their common clock signal, parallel loading, simultaneous state transition, reliable timing, and design complexity. Despite the complexity of their design, the benefits they offer in terms of speed and reliability make them a popular choice for many digital systems. So, that was a brief tour of synchronous counters, their characteristics, design process, and applications. Remember, they are the backbone of our digital world, keeping track of time and sequence.